it's Keith here, and this is lesson 12 of the multi-platform series of my Z80 programming tutorials. Today we're going to look at some more tricks on the stack. Now, we have covered the stack in the past and we've done some tricks with it. I thought now though we could really go into some details of some things that I hadn't really done in the past, and I thought we could have a look at them and see maybe some of them will be useful to you. And even if they're not, I think it's a great way of really emphasizing how the stack works on the Z80 and many of these other kind of processors. So we're going to look at a variety of tricks we can do with the stack, things that we can do manipulating call addresses, and how we can use the stack for other purposes. We're going to be testing today on the Amstrad CPC because it's got its built-in debugger, which is really going to help us step through things and see what's going on. But the principles you see today will work on other systems, so it's not a CPC exclusive concept. We're just looking at some simple sample code to show the ideas. You would want to rewrite this to do whatever you wanted on whatever system you were actually testing on. So let's go over to the code for today's example and have a look. Okay, so the first thing we're going to be discussing is parameters on the stack. So we're going to have a look at this now. So what are we going to do? Well, we're going to call a subroutine called sub1. You can see it just here. And we're going to pass it two parameters. One's a word, 2 bytes, and one's a single byte. But rather than loading them into HL and BC and things like that, we're actually going to load them by defining them alongside the actual call. So you can see our call here, and then we've got 3 bytes, a word and a single byte just here, and these are the parameters for this call. So this is a bit like a command of in our own right, sort of like this would be. These are inline parameters for this subroutine, and this is quite beneficial if these are permanently fixed, because rather than doing load HL, 1, 2, 3, 4 and LDA, 33, that would actually take up an extra 2 bytes with the LDHL part and the LDA part. So we're saving a couple of bytes doing this. So this could be an important way of you saving a few bytes if things are getting desperate, which they possibly will. It also might be more just convenient because you need those HL and A for other things. So as I say, all round this could be quite useful to you. So that's what we're going to do here. And how this works is when we call the sub, you can see what we're doing is we're loading the calling address off the stack with EX, open brackets SP, close brackets IX. So IX now contains the calling address. And then we can use the offsets from that calling address to load in our parameters here. And then we're calling the monitor just here. So let's just execute with a breakpoint here. Let's just compile this. And we will do call 1200 here. I'll just get this a bit more on frame because I'm terrible for forgetting where it is. Okay. And now we have a debugger's loaded up here, and you can see our stack here, and this value here 1207 is the return address of the function. So this is sub1 running now. So if I press F7 here, you will see now that IX equals 1207. So it has now loaded the return address from the stack here. Then what we're doing is we're loading in L and H here. So you can see that L and H now equals 1122, which is the parameters we defined just here. And then we're loading in A as well. You've got to make sure that you get the offsets right for the little endian and the order of the parameters after the call. But then once we've done that, you can see we will then be able to show them to the screen. And just like that. So you can see that everything has worked as we would expect. We've shown the values to the screen, 1122, and AF is equal to 33 there. So we've loaded those values in and we've returned without problems. Now, of course, once we've read in the data, we actually need to update the return position, because when the call occurs, the return address would be this line here, but that's not an executable command. So what we need to do is once we've got that return address, we need to add 3 to it because we've defined 3 bytes after the call address, and then swap that back onto the stack with another EX command just here. And that puts a valid return address skipping over these 3 bytes just here, which is exactly what we want in this case. Now, that's one way we can use the stack and use parameters. Another way that is quite different and really the opposite purpose is we can push parameters onto the stack, then we can call a function and the function could pull those parameters off the stack. Now this is going to be better for cases where the values are going to be dynamic. They might change every time the program runs. If this was a show sprite routine or something, then this mode might not be appropriate, but this one might be. The advantage of this is going to be that it's not needing our registers to have the correct values. Maybe we're using A, B, C, D, E, and HL for other purposes, and we still need to pass more parameters to the function. So while pushing them on the stack would leave our main registers free for that purpose. But of course, this is actually taking up more memory. So whereas this one saved memory, this one is really saving registers. This is a common trick you see with the 68,000 processors and things, where you are passing parameters to the operating system. You often see this kind of trick. But I thought we could definitely do it on the Z80 as well. I thought it'd be a good way of having a look at the kind of tricks we can do manipulating stack pointers. And so you can see we're doing it just here. So in this case, we just want to get the return address here. So we're popping off the stack into IY here, and then we're adding 4 to IY. And this is effectively moving the stack pointer down to the point where we want to set it when we return, because we want to take all of these parameters off the stack because they don't want to be there long term. So that's what we're doing here. So we've got that return address here, and we've added 4, and then we are just specifying the offsets to the parameters relative to that new return address position, using negatives here and loading those into our registers here. So if we just have a look at this one run, I will just put a breakpoint here. I'll compile this. And if we do call and 1200 here, you can see we've now got a breakpoint here. Now you can see here that the top address here is 1218. But then we've got our test values FF, EE, and DD here, which we loaded onto the stack before we ran the function here. And we want to get at those. So we're popping off the stack the return address here, because we need to keep that return address intact. So if we just step ahead, so we've got that return address. We're then loading IX with 4, because we want to offset the stack by 4 bytes, because although we only pushed A onto the stack, of course the flags moved with it, so that's still a pair. So we're then adding that to the stack pointer. The stack pointer is now pointing to the position that we're going to put the return address. So we can now load in L and H here, load in the accumulator. We'll show the results to the screen here. And then once we're done with that, all we need to do, I'll just put a breakpoint here. All we need to do is load the new IX, which is updated to jump over these parameters here. And when we step there, you can see that we are now effectively at the first byte before the call was occurred. We then push the return address, which has been held in IY, back onto the stack, and we return. And this will return us to the point that our subroutine was called just here for this return here. So that's a trick we can do. We need to make sure that our return address is not damaged in any way, but we can effectively remove 4 parameters, 4 bytes from the stack, load them into registers, and then if we wanted, use them within this subroutine. Of course, this subroutine doesn't really do anything. It's just to make a point of what we can do by manipulating the stack pointer and by reading items off the stack that we've put on for the subroutine to use. Now, in the same way as we can pass parameters onto the stack, we could also return them. So if we have a look at this function here. Now in this case, we're actually going to do the opposite. We're going to run a function, and the function is going to put some parameters onto the stack after the return address, so that once we return, we can just pop those parameters back. So we're going to call this return vars function, and you can see we're going to have 3 parameters to pop back. And this is very straightforward. All we're doing is we're popping the return address into HL here. So this takes the return address off the stack. We're then pushing the parameters we want to return, and then finally we're pushing the return address back to the top. So when we return, we can then take the 3 parameters off. So let's compile that. Let's see that in action. And if we do call 1200 here. Now you can see here, we're at this line here. Now the return address is at the top of the stack here, 124B here. And if I just do an F7 here, now that's been popped off into HL. We're then going to push our 3 parameters onto the stack here. And then finally we push the return address back to the top of the stack. and return, and then the 3 parameters we just pushed on are then available for us to pop back off, and then finally we'll call a monitor, and you can see here that 1234 has been loaded into DE, 2233 has been loaded into BC, and 7788 has been loaded into HL, and these are the parameters that we pushed on just here. So we can pass data to functions via the stack and receive it back if we wish. The stack also has another great advantage to functions if we want, and this is reserving memory as temporary store for the function itself. Now, let's say we've got a subroutine, and the subroutine needs 6 bytes of memory for its own purposes within the routine. Now, one thing that would be very simple for us to do is just define a label in our program code and define 6 bytes of zeros that would start up, and then the routine would use those while it was running. Now that might be fine in some cases, but what about if we can't spare a permanent 6 bytes like that? I know that sounds silly, but there might be cases where memory is so sparse that we can't. And the other problem is going to be, what if that is a nested subroutine, so that there might be multiple iterations of it running that are going to need the data back in later? We wouldn't want to have a nested routine that's using 6 bytes every time and there's 10 nested versions of it or something like that. So we might want there to be a situation where we can use temporary storage that completely disappears when the function runs, and the way we can do this is by allocating some of the stack for it. So what we're going to do this time is we are going to allocate 6 bytes by artificially moving the stack pointer by 6 and storing the new stack pointer in IX, and then that stack pointer we can use as an offset and read in or write to those bytes, and that's what we're going to do just here. Once we're done, we then just restore the stack pointer, adding the 6 again, and effectively those bytes have disappeared. There's no trace they ever existed. So that's what we'll do here. Let's just try this out. So you can see here we are just allocating the memory here. We've loaded in a minus here, so you can see that's converted to FFFA here. That's an easier way to add to the stack pointer, and that has moved the stack pointer up here. When we just load it in here, you can see that's now moved up to here, and then we can load in our values, and you can see those are filling into the temporary memory here. But once we're done, we just restore the stack pointer once our subroutine's finished, and they've completely disappeared. It was if they never existed, and of course, because we've not affected the stack in any way, our program just carries on as it was. So that's an easy way if we need to get a few bytes of extra memory. Now, to be honest, Chibi Akumas never did this. This wasn't an idea I'd actually had back then. This was something that I think I read in some of the documentation on the 68000 processor. So it was something that just simply didn't occur to me. So maybe it would have been handy if I'd known it, but as I say, unfortunately, I didn't know it back then. Although that said, in a lot of cases, there wasn't that kind of nesting within Chibi Akumas, and I was using a lot of self-modifying code. So where I had a few bytes needed for storage of data, they were actually in the load statements themselves. So I was modifying bytes like this within the code using self-modifying code. So maybe it wouldn't have benefited Chibi Akumas anyway, but as I say, it was a concept that just wasn't on my radar back then, unfortunately, so I didn't do it. Now we're going to have a look at something that's another interesting idea. This is something that happened in Chibi Akumas quite a lot. So we've got a little test program here. It's a case statement. The case statement is just the first example. So if we run this with a value in the accumulator here, you can see it's just returning a message saying 1, 2, or 3, and thanks for playing. Now let's have a look at the case test here, and we'll just change this to 14 while we do. So you can see that this is a very straightforward and quite boring program, to be honest, unfortunately, but it was the easiest thing I could do to make a point here. So it's now saying, hey, what's that? Because we've put in a value that's not 1, 2, or 3. So each of these case statements is ending up with a jump to thanks here. So jumping to here. And if we were in a situation where we were desperate for memory, because Chibi Akumas was, this is a 3-byte command. JP is a 1-byte part, and case thanks is a 2-byte label. So that's 2, 4, 6. And if we had 50 of these or 20 of them or something, it would start to really add up. So we might be in a case where we need to find a way of saving those few bytes. As I say, this did happen in Chibi Akumas with the code that handled the event stream. All of the processing of the events jumped back to the handle next event routine. Now, there is a trick we can do by using our knowledge of calls on the stack that might in some cases save us some memory. Rather than a jump to case thanks, if we load the address of case thanks and push it onto the stack, then any return command that follows on will effectively end up being a jump to case thanks. So our return command is just 1 byte, so as long as this push here, which would be 4 bytes, plus the 1 byte doesn't actually end up taking up more memory, which I think in this case it probably would. I don't think it's saving any at the very least, but as I say, this is just a very simple example. But as I say, in Chibiakumas there were actually, I think there were dozens of these, and they all return to the same point. And so by pushing it onto the stack and using a return, that was simulating a jump, but in a single byte command. And so that's a good way you can use it. And it's also a good point about how you can misuse the return command to jump to a location, because there may be cases where you want to jump to the value in BC, but you can just do push BC and return, and that is the equivalent of jumping to the address in BC. You might have different places you want to jump at a later date at all of these, and you could just push it onto the stack. But in this case, what we've done is all of these returns are being used as a jump to case thanks, because case thanks was pushed onto the stack just here. Now, there was one case that didn't want to jump to case thanks, so we need to get rid of that address to jump to, and we've done it by popping just into any old register, HL in this case, before the return, and that effectively skips case thanks and just returns as it normally would. Now, we'll run this, but unfortunately, because it's identical in function to the previous example, we won't actually see any difference, but you can trust me, it does work. So it works the same because it's the same function. I'm just using a push of an address and then a return instead of a jump this time. Now, that's, as I say, the main time you're going to want to know about that is if you're desperate for memory. So being as we're discussing jumping and calling and desperation for memory, I think it's only appropriate we discuss the RSTs again. We have covered them before, but I'm going to discuss them again because it's very related to this. Now, on the Amstrad CPC, RST6 is reserved for us. If you're working on a ROM-based system, like the Sega Master System, then you can basically do whatever you want with all of them. But an RST is a 1 byte command that will jump to a memory address within the low area, and RST6 or RST and 30 in hexadecimal is the free one that we can do whatever we want with. So what we can do is we can program this to do the equivalent of a jump, and that's what I've done here. Now what we're doing here is we've got a command called RST test here. It's loading an address from the following bytes like we saw earlier. It's just loading in 2 bytes here, and then it's jumping to a print string routine to show to the screen. So call RST test of text1 is effectively the same as load HL comma text1 call print string. Now you've got 2 bytes here, you've got 2 bytes here, 1 byte here, 1 byte here, so that's 6 bytes. Now this call here would just be 5. So we've kind of saved 1 byte, but it's not great. But by creating an RST that does this for us, this is just a 1 byte command, and this is 2 bytes here, so this is 3 bytes. So this is effectively half the size of this, which could be seriously important if you're really desperate for memory. So as I say, this is something that you might want to consider where you don't need the speed so much, because I'm afraid this isn't, the RSTs aren't faster, but they do work in a single byte. And we've almost arguably created a command of our own. We've basically created a print string command called RST30 or RST6, depending on your assembler. RST6 will work on WinApe, but it won't work on VASM, so I'm using RST30 here. It's the same functional command. So how do we define our RST? Well, all we need to do is change the memory address that RST uses, memory address 30 in hexadecimal, and there's 8 bytes per RST, which really isn't much. It's really only enough for a jump, really. So I'm just loading in a jump command, which is hexadecimal C3. That's the bytecode for the jump command, and then I'm loading the address of RST test, and I'm just writing those bytes to the memory address hexadecimal 30 and the 3 consecutive bytes, and that programs RST hexadecimal 30 or RST6 to jump to this label here, which is doing the print string work. So if I just compile this and I do call 1200 here, you can see 1, 1, 2, 3, thanks for playing. And that's because we did a print string of 1 here, another one of 1 here, 2, 3, and then the thanks message here. So you can see our sudo print string command via the RST has worked indeed. And as I say, that was something I did use in some desperate cases where I had a lot of different places in a chunk of code that would need to run the same command at some point. I would define the RST6 with that command, and then I could use that as just a single byte command in those places. So again, it's a trick in your arsenal if you are desperate for memory, which, as I say, if you're doing a complex game like Chibi-Akuma's, it could happen. You would think it's ridiculous to be desperately saving bytes like that, but I'm afraid it's entirely the case that will happen to you. Now, the other one I'm going to discuss, we have covered it before, is stack misuse. This was covered in the main series, but I thought it was sufficiently important that we should cover it again. Now, this is where you are actually using the stack pointer, not for the temporary storing and recall of data or for subroutines, but actually as a fast data reader and a fast data writer. You see, the stack pointer and the stack reading and writing commands are far faster than other commands. If you look at them byte for byte, if you're reading in byte pairs, they're very fast. So when you are looking to shift very large amounts of data, like when you're filling a screen, when you're transferring a sprite from memory to video memory, that kind of thing, you want to try and use the stack pointer in some way, either as the writing component or the reading component within this, because that's how you can make things faster. And in all honesty, whenever you see an 8-bit game that's uncommonly fast on the Z80, you can be pretty sure it's doing this in some way, whether it's filling the screen with it or whether it's reading its data, because this is one of the tricks you can do to really get things fast. Now, we're using the stack pointer. We're pointing the stack pointer to either to the start of our reading data and we're popping off values along, or the end of our writing data and we're pushing data filling over the destination. So in this case, I'm actually using it as a reader. I'm going to read the screen, and then I'm going to write it to one block down because of the organization of the CPC screen. I thought this would be nice and easy. So we're going to actually copy the entire screen over itself by reading in using the stack pointer here and then writing the bytes with these two commands here, and this will be faster than if we just used an LDIR or something like that. So of course, while we're messing with the stack, we can't do any calls, we can't do any pushes or pops for any other purpose, with some very clever exceptions which I've gone over in my interrupts tutorial. I'm not going to go over it again here, but generally speaking you can't. So what we're doing here is we're backing up the stack pointer into IX here. Unfortunately there's no direct command to do that, and then we're restoring it just here, and that will effectively back up and restore the stack pointer. We then point the stack pointer to some of our screen. The destination is the top of the screen, the source is one block down, and then we are just copying along. So if I compile this, and if we go to our screen here, and if you watch carefully, and I do call, well actually let's move up because otherwise we'll get a scroll. So if I do call 1200 here, you can see the entire screen moved up a bit and some corruption has come, which is the bottom usually not visible area of the screen. And if I just do that again, you can see we've moved up again, and so on and so forth. So I mean, as I say, the point isn't moving the screen around. The point is that that happened very quickly, and we have moved a very large amount of data there, and the point is that the stack pointer is the absolute fastest way you can get the data to transfer on the Z80. So if you want to make a fast game, this is how you want to try and find ways of doing this, either for clearing your screen, drawing the gradients in Chibi-Akuma's was done with this, the sprite routines use this. As I say, it's a really essential tool if you want to make a game that stands out on the Z80 systems, because it's so fast. So there we go. So that's what I wanted to cover today. We've covered a variety of little stack tricks that I've learned over the years. There's probably some more that I don't know. So if you've got any ideas of ways that these routines can be used, or ways the stack can be used rather, to do things that are really handy that you think on the Z80 systems, please let me know. I'd love to hear some more, and maybe you can give me some ideas to cover for future tutorials. Anyway, I hope you've enjoyed this. I hope you found it useful. Yeah, as I say, the ideas we've looked at on the CPC today, but they're all just concepts and you can use them on any system you want. You'd obviously need to write the code to do the exact things you need. So the example is available for download off my website, but it's not going to be useful in its current form. They're just very simple samples on learning ideas of ways of using the stack. I hope you found it interesting anyway. Thanks for watching today, and goodbye.